Okay, what we're looking at now is a fairly complicated maximization. It's called linear programming. So if you ever want to look up some help on this, that's the name of it mathematically. So it says maximize p subject to the following. So p is just this equation 4y minus 3x. And what I'm going to do is I'm going to sketch a graph of these four inequalities. Our first constraint is x is less than or equal to 4. And when I graph these, what I tend to do is I just put an arrow that kind of points to the side that satisfies the inequality, and then I kind of pull it all together at the end. Y greater than or equal to 0. So that's just going to be this line right along the x-axis. Okay, and got a couple of equations I need to solve for y. On the first one, if I just subtract x, I get y is greater than or equal to negative x plus 4. And let me do a little algebra on this one. Y is equal to 1/2 x plus 1. Okay, so I'm going to graph y is greater than or equal to negative x plus 4. Oh, and by the way, these are always solid lines. It just seems to work that way with these problems. Y is negative x plus 4, 1, 2, 3, 4. So there's my y-intercept. And 4, so I'm going to go down 1, right 1, and that's going to intersect right there. And that's y is greater than that. And now my last equation is y is, and I drop my inequality, let's pick that back up again, is less than or equal to 1/2 x plus 1. So here's my, let me do a color. Here's my y-intercept. And then I'll have up 1 over 1. So this will go that way and below. Okay, so in between all of this is this particular area. It's where, and it's a little bit clearer if I write this here and the blue one here. And then the black one is pointing left as well. So what we do is we have to find all three intersections on this problem. We need to know where these two equations intersect, these two, and these two. And with those coordinates, then we finish our analysis. So the red line is y equals less than or equal to 1/2 x plus 1. The green line is negative x plus 4. I'm labeling with the lines because I have to find the intersections. Okay, so my main intersection is between the two lines, negative x plus 4 and 1/2 x plus 1. The way to find that intersection is just put these two equations equal. I'm setting their y's equal and finding out what the x value is. So do some solving steps here. Now I'm adding fractions, so I'm going to write that 1x as 2/2. And now let's subtract 1. I get 3 is equal to 3/2 x. Let's use the reciprocal. And it looks like we get x is equal to 2. And what's my y coordinate? Well, I can plug it into either one. So if x is equal to 2, negative x plus 4 is equal to y. So negative 2 plus 4 equals y, it looks like y is equal to positive 2 as well. So this intersection in the middle is at 2, 2. It's fairly easy to read the other intersections off of the graph. The intersection here is going to be at 4, 0. And I also know that right here on the third, my x is equal to 4, so I'm just going to calculate 1/2 4 plus 1, which gives me 2 plus 1, which is 3. Okay, so I have these 3 intersections to take a look at. And I'm going to do that. I'm going to finish up my analysis over here. So I've got 2, 2, 4, 0, and 3, 4. And they're asking which will maximize, I think. Let me go back and check. Maximize P subject to the following. Some of the problems they ask to minimize. But you'll see what we do. I just take that equation they gave, negative 4y equal minus 3x. And I substitute each of those ordered pairs in there. So 2, 2. We get negative 4 times 2 minus 3 times 2. That looks like a big negative of negative 8 and negative 6, which is negative 14. And at 4, 0, we get negative 4 times 4 minus 3 times 0, which looks like a negative 16, even more negative, and then we get 3, 4, which gives me negative 4 times 3 minus 3 times 4, which gives me 0. So it's not a very satisfying answer, but the maximum amount comes from the 3, 4. Okay? All right. I'm going to end this video. See you on the next.